The reason that I like this problem is because it's a combination of inclined planes with friction, with springs, with work and energy, and an Atwood machine to boot. So it's like it's got kind of everything together. So this is kind of a really good review problem. I'm going to call this right here M1 so we can make this very general. I'm going to call this one M2. I'm just going to call this theta. What we have here is a 20 kilogram block, that's M1, is connected to a 30 kilogram block, that's M2, and it's connected by a spring that passes over a light frictionless pulley. Whenever you see the word light on an AP exam, a light in this case means zero mass. Does that make sense? And it's got frictionless. They might say a very slippery pulley when they want you to do it frictionless. It's connected to the spring that has negligible mass and force constant of 720. What variable is that? Let's just label that right now. When it says force constant, what do they mean? What letter?
The force constant, isn't that K?
Lowercase k of the spring is equal to 720 newtons per meter there. And then the spring is unstretched when the system is shown in the figure, so they're saying it's unstretched here. The incline has got mu k is 0.2. The 20 kilogram block's pulled 16 centimeters down the incline. So this is pulled this way 0.16 meters, right? I'm going to do everything with SI units. Whenever you use energy, kind of important to get to meters, kilograms, and seconds. And so that's pulled down 0.16 meters, which means this goes up 0.16 meters. It's giving us actually a bunch of stuff that we don't need. Doesn't matter how high above the floor it is. That's not going to matter. And what we want to do is we want to find the speed of the block when this 30 kilogram block is basically when it returns back down to where it started. That's when we want to find the speed. So we want to get V final at that time. And you can just write V final. I've put a little F to accentuate that, but just V is also the symbol for V final. A lot of kids will make the mistake of saying this is our initial situation. It is not. We haven't started the problem yet until
0.16 down.
Yeah. That's we want to start it when it's that far down. I've pulled this down. It's to this level here. I'm just going to mark that level right there with that dotted line. This is like the equilibrium point of the spring when it was unstretched. It's been lifted up to this point right there, a total of 0.16 meters as well. Now, what I want to do, and what you should always do when you're doing energy problems, is we got to define where our zeros are. We can actually have it be different places for different objects in different parts of the system. Let's start with M1. This is now our initial situation right here. Where do you think would be a good place to call 0 for M1's gravitational potential energy?
Can we put it like where we start, like 0.16 down?
That makes sense to me because that is the lowest. This is the lowest height. I'm going to call this H1 equals 0. I can make different heights be 0 for different objects simply because all that matters is the changes of height for potential energy changes. Because you can set 0 wherever you want. I'm going to set it right there for this thing. How about for this mass, M2? Where would you like to set that 0? I like the lowest point to be 0 simply because we'll never have any negative gravitational potential energy. So I'm going to make this height 2 equals 0. Okay, there we go. Now, where should we make 0 potential energy for the spring? Different kind of potential energy now, spring potential energy. Where would you like to make 0 for that?
Would that be like when the spring is at equilibrium, so when it's not stretched out?
Exactly, and you really kind of have to do that, and that's down here. I'm going to set this also US is equal to 0, the potential energy of the spring, which means, and by labeling H there, this is UG1 equals 0 there. This is US, and also UG2 is equal to 0. So the reason you got to choose the unstretched position for the spring, because if you set some other arbitrary position as 0 spring potential energy, you might get negative potential energies. In fact, you will. The lowest potential energy it ever has is when it's unstretched. Every conservation of energy problem can really be written starting this way. E initial plus work non-conservative equals E final. And non-conservative work is work that's done by things like friction. If you're doing work, that's non-conservative. The conservative forces we have are springs and gravity, and you can see those are going to be involved here. We may have some non-conservative forces which would do non-conservative work, so that's why that term is there. Now, let's go ahead and just be very, very general about what forms of energy we have in this initial situation.
Gravitational potential energy.
Okay, what I'm going to do is I'm going to list it for both. I'm going to list UG for object 1 initial, and I'm going to list UG for object 2 initial. Now, I like to put them all. Some of them are going to come out to be 0, but I like to make sure I haven't forgotten anything, so I like to list them all. So we've got those gravitational potential energies for both objects. Do I have to do that for the spring too, like figure out gravitational potential energy for the spring itself?
Yeah.
Well, notice that in the problem, just to review that, they did say to a spring that has negligible mass. So we don't have to worry about the gravitational potential energy of the spring itself. Are there any other forms of energy present whatsoever?
Yeah, the spring potential energy.
Yeah, so I'm going to call that US. There's only one spring, so I don't have to number it. US initial. Okay, cool, we got that. Is there any kinetic energy at this point? No, we're releasing it from rest, so it's good. The next thing we got to start thinking about is there any non-conservative work being done? And the one thing I should have indicated on here, I'm going to draw it right on here, they did give us mu k for that surface. So that's kind of a hint. What kind of work non-conservative is there going to be?
Friction.
Yeah. Now, you could say plus work of friction and then allow that value to be negative, or you could say minus and then just make sure you don't add an extra negative. I'm just going to do the most general case, which is plus. It probably will come out negative, so we'll deal with that. That is the work of kinetic friction. I'll just call it work of friction. And then E final. Now, E final, we have to remember when this is done, what's going to happen is this spring's going to pull this back down. This M2 is going to end up right there, right? The spring is going to end up completely uncompressed like that, back to its initial position of equilibrium. And then our block 1 will be somewhere right about there. So that's our final situation. What forms of energy are we going to have in the final situation? I'll actually try to keep this in red.
The gravitational potential energy of object 1.
Okay, right. So I'm just going to write UG final of 1. I'm going to write UG final of 2 as well, even though if you're thinking that may zero out, you're right. Is there any spring potential energy at the end?
No.
Because we're returning to the unstretched position right there, there won't be. Is there any other kind of energy, though?
Kinetic energy?
It is going to be moving at that point, so I'm just going to call it K final. Now, that is the most general equation that we can get for this problem, and now I'm going to start simplifying it by zeroing things out. All right, so for starters, UG1 initial. Can I zero that one out?
Yeah.
Yeah, it started right there at height equals 0, so that's 0. UG2 initial, is that 0?
No.
No. US initial, the spring potential energy initial, is that 0?
No.
Work of friction, there is going to be some friction. That's not going to be 0. UG final 1. Will UG final 1 be 0?
No.
No. UG final 2?
Yes.
Yeah, that will be 0. So again, I'm just trying to get this more and more specific and more simple. So now here's our general relationship. UG2 initial plus U of the spring, potential energy of the spring initial, plus work of friction equals UG final 1 plus K final. By the way, every single one of these steps will typically get you a point on an AP exam. So it's really helpful to show all the steps, because even if you get something wrong, you still got all the points from above. When you start plugging in numbers right away, you basically lose your chance to get all those points. Put in numbers at the very end. Let's go ahead and express these a little bit more specifically. And taking a look at this, how could I express UG2 initial, which is the potential energy of this thing initially? How could I express that?
mg times h, or times your...
Yeah, and I'm going to call this distance right here, there actually is probably a good reason to call it x. as we'll see. Now you say that's up and down. Shouldn't we call it y? You could call it y. You'll see in a minute why I'm going to call it x, and it's because I'm thinking ahead and I've done this problem a bunch of times. Okay, are you okay with calling that x? It's just some distance, right?
Yeah.
Okay, cool. So now that means that our UG2 initial is going to be, as you said, M2G, and then I'm just calling that x. Is that correct for my initial potential energy of object 2? Yeah, because I called this point right up here 0, so that's correct. US initial, or what would I express that as?
Half of k x squared.
There we go. Now do you see why I thought ahead and used that x?
Yeah.
Because a lot of people will just go mgh 1/2 kx squared, and they don't even realize they added a variable, even though we don't need to add a new variable. There's that. Now, work of friction, I'm going to just kind of break that down step by step. If we look right up here where the friction is happening, as this is being pulled up the hill, Fk is going to be down that way, right? But notice that the displacement, which you could call r or x or whatever you want to call it, actually is going to be x. Notice that for this object, those are in opposite directions, right?
Yeah.
So if I could do the dot product, I mean, you could write it as Fk dotted on our little x vector, with this being a real dot product, which means multiply f by x by the cosine of the angle between them. But I'm just going to simplify this by one step ahead of time, and I'm just going to write it like this. First of all, that angle between the Fk and the x is going to be what? What's the angle there?
0.
It's actually not 0. Yeah, because of this, it's 180. The cosine of 180 is what?
-1.
Yeah, force and displacement. If they're in opposite directions, the force is doing negative work. That's another conceptual thing. So we could have just added a negative. Negative. I'm going to put in Fk times x, because that's also the distance x, right? Yeah. That dot product gives us that negative sign right there. You could put in cosine of 180 and it would come out negative as well. And then how can I express UG final of 1? Now this is where it gets a little bit messier. And what I'm going to do is I'm going to over here just redraw that whole picture so we can just see just this part of the picture. Okay, here's where the object M1 started. It moved up this way. So here's where it is later. This distance from there to there is x. This is angle theta. Here's the line where it started. Here's the line where it ended up. Right there. What is that new height? I'll call it delta y of 1. Hint, what is this angle?
Theta.
That's also theta. This side right here is x, right? That's x. What's this side?
X times sine, that's theta.
This is x sine theta, right? So now I can express UG final of object 1. How would you write that, you suppose?
Mass times g.
Okay, and we got to make sure we use M1 times g.
Times x sine theta.
Right. And then how can I express K final? I want to get as specific as I can here.
Half of the mass times velocity squared.
Okay, you've got the right idea. Let's go ahead and get as specific as we can. What am I going to put in for the mass here, since both objects are moving?
Both of the masses?
Exactly, M1 plus M2, right? And this is times V final squared. And now we're getting ever so closer here, getting ready to finish this up. I'm just going to rewrite it one more time. The work done by kinetic friction. Can I get more specific about any of these things in there?
Yeah, you can change the Fk to mu times the normal force, which is
cool.
M times G.
Very close. It's not quite though. What I'm going to do, I'm just going to write out the expression. I use little n for the normal force. You could use F sub n as well. And then x, there it is right there. It's mu k times n times x. Very common mistake. Let me just go back up to this. In this situation right here, is the normal force mg?
No.
No. It's a Newton's laws problem to show this, but the normal force is going to be mg times cosine of theta. This is the normal force right there. Does that ring a bell from inclined planes?
Yeah.
Okay, and make sure you know how to get that as well. But there's our normal force. And then don't forget the x here, because everyone, you write out a big expression like that, a lot of people forget, oh, it's work. It's got to be a force, which this whole thing is, times the displacement or distance there. Okay, we don't forget our negative. We got that right. And then we've got this is equal to m1gx sine theta plus 1/2 m1 plus m2 times v final squared. The question is asking, what is v final, right? Okay, so let's go ahead and solve. m2gx plus 1/2 kx squared minus mu k mg cosine theta times x minus m1gx sine theta. And then now I've got all this left. So by multiplying the whole thing, and don't forget to multiply the whole thing by 2, that will then multiply this side by 2, and I'll have, let's go ahead and, what's the last step I do? I got rid of that by multiplying both sides by 2. How do I get rid of this thing?
You could divide it.
Divide that. And then this is m1 plus m2 on the bottom. Now I got rid of that, and then how do I find v final by itself?
Square root.
Square root of this whole mess there. And that is your solution for the final speed.